So we mostly talked about polarization last time. I just want to add a few more things. The main mechanism I talked about for polarization was this device called a polarizer, which is a manufactured piece of material. But this does have its place in nature. This is not something that we started worrying about when Kodak made the polarization material. In fact, human beings are one of the animals in the animal kingdom that cannot sense polarization, but other animals can. So if you want to experience polarization, you have to walk around with a pair of polarized sunglasses on, and then you'll start to notice it all the time. So let's talk about how it comes out in nature. Let's say you have a flat surface. So this is some kind of surface, and you send sunlight down to interact with the surface. So that's the direction of travel of the light beam. That's, by the way, is called the light ray, and very shortly we'll take a look at a bunch of phenomena with light where that's really all we need to do is talk about the direction of travel, so we'll just use light rays. We'll also very shortly talk about the fact that we generally talk about how light comes in to interact with a surface in terms of not the angle with respect to the surface, but the angle with respect to the normal to the surface. That's just by convention. And let me suppose that I have unpolarized light. So unpolarized light coming from the sun, that of course wiggles in all directions. So when I draw this, it means that some of the light comes in like this, some of the light comes in like this, some of it's diagonal. There's a little bit of everything in equal amounts. But it turns out that when light reflects off a surface, not all polarizations survive equally. When light reflects off a surface, you will find that what is represented most highly in the polarization that's reflected is polarization that's parallel to the surface. So since this is a horizontal surface, what you will get most is the horizontal polarization. So light has a tendency, light tends, so reflected light tends to have more polarization that is parallel to the surface it just reflected off. Okay, so if you bounce light off a horizontal surface, you'll get more horizontal polarization. If you bounce light off a vertical surface, you'll get more vertical polarization. And that's not to say that the other polarizations aren't there, but they're generally much less represented. So there might be a little vertical polarization, but some diagonal polarization. But what is most represented is horizontal polarization because it bounced off a horizontal surface. Now I guess I can say a few brief words on why that is, if it's helpful. The reason why is that the process of reflection is the process of the electromagnetic waves actually being absorbed by the surface and then put back out by the surface. And so there's actually, at this point where the light reflected, there's actually wiggling of the charges that are inside the surface, that make up the surface. And as you can probably imagine, if you're a charge, it's going to be a lot easier for you to oscillate in the plane of the surface than oscillating up off the plane, right? So it's a lot easier to oscillate in the plane where the material is than to jump up off the plane where the material sits. So it's a lot harder for charges to oscillate vertically on a horizontal surface. So the charges tend to oscillate more easily horizontally, and that's why on a horizontal surface, and that's why horizontal polarization is what they then output more frequently. Now, that's not to say that there isn't some of the other ones, they're just a little squashed. Light will generally, as we'll learn, tend to reflect at equal angles, and so we will get some light over here. Light tends to reflect at equal angles with respect to the normal. But the light that we get reflected is, so this is reflected light, is not necessarily the same as the incoming light in terms of the polarizations represented. So, and I guess I should mention that there's one specific incoming angle where not only is the light highly polarized, it's perfectly polarized. That's something called Brewster's angle that I'm not going to talk about in this course. Maybe it's mentioned in your book. But I do want you to understand that for a wide variety of different incoming lights, the reflected light is quite polarized, parallel to the reflecting surface. So, if you want to block that reflected light as much as possible, you put your sunglasses on, your polarizing sunglasses, and which way do you want your transmission axes to be? If you want to block as much of this as possible. You want them vertical, that's right, because if the light is mostly horizontally polarized, then you want the transmission axes to be vertical. So if you buy a pair of polarized sunglasses, you can rest assured that the transmission axes in the two lenses are vertical. The reason why is that they reduce glare. Glare is reflected light. So you generally look at things through your sunglasses, like maybe the road or a lake or the ocean, things that are horizontal surfaces, and you're trying to reduce reflected light off of them. So because you tend to look at horizontal surfaces, you want your transmission axis to be vertical, okay? But that, of course, means that if you were to tilt your head with your sunglasses on them, so that the transmission axes were now horizontal, you would see more light. So that's one thing you can try, is if you're getting a nice glare reduction from your polarized sunglasses, you can go like this, and you can see that the brightness will increase when you tilt your head. Has anyone ever tried that? Okay, if you get a pair of polarized sunglasses, you start to really notice polarization all the time. So for instance, you're pumping gas, and the gas is an LED, gas display is an LED. You can go like this and get it to turn black. Okay, you can, for instance, if you look at a digital watch the wrong way, it'll turn black, things like that. Now, I might, of course, address why is it that when you put on a pair of polarizing sunglasses, everything doesn't go black entirely? Well, obviously there is still some of the other polarizations, and if you get any direct light, well, that's unpolarized, period. So you're going to get some of that. So it's not like when you put on polarizing sunglasses, everything's totally goes dark, right? And I should say that many animals, insects, they see polarization. So they can actually even use it to navigate. So if you ever get a pair of polarized sunglasses, sometimes you can even look up in the sky and tilt your head like that, and you can notice that the brightness of the sky is changing. The reason why is because light, if you're not looking directly into the sun, which I don't recommend, if you're looking anywhere else at the blue sky, the reason why you're seeing blue sky is because of light being reflected off the back of atmospheric particles. So you're getting reflected light when you're looking at blue sky. And depending on what angle that reflection is happening between you, the sun bouncing off the atmospheric particle and coming to you, that may be an angle where the light coming to you is highly polarized. So you can look in different parts of the sky and start to see the different parts of the sky turn more black than others when you rotate your glasses. And there's some animals that can see that with just the naked eye, and they can use it to navigate. Okay. Have any questions on that? Okay, so I think that should wrap things up for polarization pretty well. So you'll try some of this out in lab. You will try looking at direct incoming light that's unpolarized, and you'll notice that the polarizer doesn't do much to it except dim it. But then I'll also have you look at light that's bouncing off a surface, and you will see that it's highly polarized, and you can actually make it go black by turning the transmission axes of your polarizer the right way. I think I also noticed that the demos in general for the polarization stuff were hard to see on the camera, so I'll I put them out so you can play around with them. They're on the front table during your lab. In addition, there's one advanced polarization thing. It's beyond the scope of the class, but it's just really cool. There's a piece of polycarbonate, which is a type of plastic, and it might not look like anything, but when you look at it under polarized light, you see there's a whole hidden world of polarization that you can see there. And in fact, polarization is affected depending on the color. So you get some really crazy stuff when you look at that under some polarizers. So I put that out as well. Okay, any questions on polarization before I move forward? Okay, so we're going to just glide right into the next topic. So I kind of already hinted at some of the things that we're going to do. We're going to move into the study of geometrical optics. So geometrical optics, the name, the geometrical label, implies that the only thing we really care about is the direction of motion. So rather than drawing it as a wave, we will just draw it as a ray indicating the direction of travel, and that's really all we need. Later on, we'll come back and remember that the light is a wave and do topics that require us to remember that. That's another topic called physical optics. Okay? But for right now, we're going to focus on just drawing the light as an arrow. And to start with, I can go back and kind of just recap what I was talking about over here. Generally, when we're talking about light interacting with a surface, we measure the angles relative to the normal to the surface. The law of reflection is really easy. The law of reflection is simply that whatever angle you come in with respect to the normal, so that's called the incoming or incident angle. So that is exactly the same as the reflected angle. So you basically bounce off at equal angles. So this is the incoming or incident. Either one, they're just two different words. And this is the reflected angle. And that's it. So that's really straightforward. There's nothing to it. But it turns out that when light comes in and interacts with the surface, there's a couple different things that can happen. Some of the light might reflect, but some of it might also pass through into the material. So the light beam might actually split, and this is called a refracted beam. So generally speaking, when the light, the energy carried in the incident beam will split, with part of the energy going into the reflected and part of it going into the refracted. Now I should tell you right off the bat that it is well beyond the scope of the course for you to calculate what percentage of the incoming energy goes into which one. It's generally not split 50-50. Okay? The brightness and energy is not split 50-50. And in fact, it depends on the incoming angle. Okay? So I should mention that it is beyond the scope of this class to calculate how the incoming intensity is split between the reflected and refracted beams. Question?
Would it also depend upon what the surface is?
Yes, it will. So it depends on both it actually depends on what material you're coming from, what material you're going to, and it depends on the angle. So all things that we do not want to be messing with. So the only thing I want you to just understand is on a conceptual level that of course energy has to be conserved. So the reflected and refracted beams, their energies are going, the energy that's carried in them is going to add up to the intensity that came in, right? So there's one exception, and that's something called total internal reflection, and I'm just going to put the abbreviation there for now. I'll get back and discuss that in some detail. that is when it turns out that one of the beams gets 100% and the other one gets 0. Okay? So if you can see the words total, it says total internal reflection. So if you take out the internal for a second, this is distracting total reflection, right? So it suggests that the light is totally reflected and not at all passed through into the material. Okay? So we need to now address refraction. What about that light passing into the material? Well, before we even get into the rules about angles, so we need to talk about the refracted angle, and I'll call that theta sub t because I can't use r for both reflected and refracted. So I call it t for transmitted. It's transmitted into the material. Now, before I even talk about the angles, how does the initial angle relate to the transmitted or refracted angle? I do need to do a little bit of background because we haven't really even discussed what it means for light. What happens to light when it goes into a material? So let's just do a little background on that. So light passing into a material, how does that work? So let's go ahead and draw a borderline between a vacuum where light is able to travel completely unimpeded. There's nothing for it to have to travel through. And it's going to enter a material. So we'll go backwards for a second. This is not going to be geometrical optics. I'm going to have to address what happens to light when it enters a material. So I better put the waviness there. And out here, we call the light speed c. That's a special character we use for the speed of light. It has a frequency f0 and a wavelength lambda naught. I guess I can label the wavelength here. Crest to crest, that's the wavelength. And let's talk about what happens when it goes into material. Now, if you have stuff that you have to go through, what might you think would happen to the speed of light? Do you think it's going to slow down or speed up? Slow down, right? It's going to have go through some material. In fact, what happens with light when it's passing through material, it's sort of passed along. It's absorbed by one atom, given to the next, absorbed by that, and given to the next, and so it's going to create a little bit of a time delay in the light traveling. So if we talk about the speed of light in a material, which we're going to call v sub n, we switch back to good old letter v for speed, and then I'll tell you what the n is for in just a second. It's definitely going to be less than the speed of light in a vacuum, which we have as kind of a sacred character as c. That's the speed of light in a vacuum. So you're going to slow down. So now let's look at what happens to the other things. Well, what happens in traffic to the spacing of the cars if there's an accident? They bunch up, right? So that's exactly what happens with the wave. It's going to bunch up. Because basically, the crests that arrive from the vacuum can't get away as fast, so they tend to bunch up. So the wavelength tends to be smaller. So the wavelength in the material tends to be smaller than it is in the vacuum. They tend to bunch up. However, if I were sitting on the borderline between these two surfaces, so there's my physics eyeball in the sky, imagine it totally right at the interface between the vacuum and the material. If I were counting frequency, crest, 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 the rate at which they arrived from the vacuum is, of course, exactly the rate at which they enter the material. So the frequency is actually the same. Oops, let me label it the same direction. So the frequency in the material is the same as in a vacuum. So if you counted crests over on the vacuum side, you get crest, 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 crest. If you count them over here in the material, you get crest, 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 crest. Now you might say, well, how can the frequency be the same if the wavelengths are so bunched up together? Why wouldn't you get a higher frequency? Well, remember that the whole wave is slowed down. So yes, the wavelengths are more bunched up, but they're also traveling slower. The frequency is actually exactly the same. And it has to be, because if you're sitting on the interface between the two, well, the frequency at which crests arrive from the vacuum is also the same frequency that they leave into the material. So let's go ahead and work out the details. Well, the way we characterize how much light slows down is with this thing n. So that's why everything in the material is labeled sub n, subscript n. N is called the index of refraction. It's the property of the material. Property of the material. And that property informs us how much does light slow down when you enter. So by definition, it's equal to 1 for a vacuum, and it's greater than 1 for everything else. Because you can notice the way it's defined is as dividing the speed of light in a vacuum. So if you want to slow down, then you have to divide by a number larger than 1. And I should also note that it is a dimensionless or unitless number, because it's just a divider to get from the speed of light in a vacuum to the speed of light in your material. So there's no units at all. So let me give you some examples. For air, for instance, the n value is 1.000293, which is barely bigger than 1, so light barely slows down in air. And it's no surprise, because as you know, gas is mostly empty space, so it's mostly the light is traveling completely unimpeded, but once in a while it will run into an air molecule, get absorbed and shot out again, and that'll slow it down just a little bit. Okay? In fact, this really, we usually take as being approximately equal to 1, because it's not worth including that precision in the 4th decimal place. The only exception that we might make is if, of course, we're talking the difference between an air and a vacuum, then we have to acknowledge that there's a difference, right? So there is a little bit of a difference in the n value of air in a perfect vacuum. Now, if we get into other materials, let's say water, liquid water. The value of water is 1.33, so there's a substantial reduction in the speed of light. And diamond, which is another transparent material, but as you know, quite dense, and that'll slow light down quite a bit. In fact, the n value is 2.42. So if you have light traveling in diamond, it travels less than half as fast as it does in a vacuum. Okay? That is actually one of the highest n values of naturally occurring transparent materials, and that'll actually have, it's part of the reason why a diamond, what gives diamond its value. In a lab, you can manufacture things that have n values in excess of 1 million, and you can slow down light to this, which is again the speed of light in a vacuum is the fastest speed possible, but you can slow down light so much that you could outrun it. Okay, so there's a whole technological movement in the quote-unquote slow light. There's applications for slowing down light until it's moving at just crawling speeds, okay? But they require special materials that are manufactured to do that. So now that's how we quantify how it slows down. Let's work out the details while we're at it, even though we won't need them in geometrical optics, where we're just talking about light rays, but let's talk about what are the details for the wavelength and frequency. So I go ahead and I use V equals F lambda. That's my master equation that relates these guys. And I see that if we're going from a vacuum to a material, this is reduced by n, and the F is fixed. So what does that mean then about the wavelength? How much does that get reduced? By n, right? So if F is fixed, then whatever happens to the speed happens to the wavelength. So we could also say that the wavelength is reduced by n. So So when you go into a material, the light slows down, by factor n divided by n. The wavelength is smushed, compressed by a factor n, and the frequency is the same. Now this brings up an interesting point because when light travels from one material to another, the thing that you can count on as being preserved is its frequency, not its wavelength. So wavelength, you have to really be careful. So for instance, we talked about visible light. Visible light is 430 to 750 terahertz. Roy G. Biv, going in this order. And you can always count on that. 430 terahertz is always red, 750 terahertz is always violet. Now these particular frequencies correspond in a vacuum with red being 700 and violet being 400, but those frequencies do not always correspond to those wavelengths. So if someone says, well, you can't see 200 nanometer light, it's too low of a wavelength, well, you can say, I can see it just fine. Just send it to me. If that's coming to me in a material where n equals 2, so let's say, suppose n equals 2, then those frequencies will correspond to wavelengths which are half as much. So let's put in n equals 2. Then this will be 300, red will be 350 nanometers, and violet will be 200. Okay? So visible light corresponds to particular frequencies always, but those frequencies do not always correspond to certain wavelengths. Okay? So whenever you hear anyone saying that visible light is 400 to 700 nanometers, they're talking about the vacuum wavelength, not just any old wavelength. Okay? Are there any questions on that? Okay, so I think you have a few questions on your homework that asks how is the frequency and wavelength and speed related when you go into material. But the only thing I really need for geometrical optics so that I can go back to refraction is the fact that light slows down. Okay? So that is going to inform how the bending of light happens. It's going to turn out that the refracted beam is going to be bent. And the reason I'm going to motivate that for you is because it slows down, it has to bend, and I want to tell you why that is. Okay, so let's talk about that. So let me not talk about light, but let me talk about just the general principle that can be applied to light and many other things. Fermat's principle of least time. For this, I'm not going to explain why this is the case, but it's going to be kind of an axiom. And it's what its statement is very simple, is that light will always take the path of whatever is the quickest, so hence least time. Okay? So if you're trying to figure out how light is going to move, what path it's going to prefer, it's going to do whatever is the quickest. Now, as we will discover, whatever takes the least amount of time may not necessarily be the shortest distance. We're used to, of course, associating, if you want to get somewhere the fastest, you also go in a straight line. But that is not always the case. Let me give you an example. So I'm going to be at the beach. Here's my beach. Here's my water. And these represent two different materials, sand, walking on sand, and swimming in the water. But human beings have different abilities to move rapidly or not, okay? So everybody can run on the beach faster than they can swim in the water, okay? So let's say we have a drowning swimmer over here that needs help, and we have a lifeguard over here. One of those pontoony things, right? So let's evaluate different strategies for getting to the drowning swimmer, and obviously here the least time is really important. So you might say, well, at first, what's wrong with going like this? Well, you're not really taking advantage of the situation because you can run much faster along the beach than you can swim in the water. So then you might say, well, why don't I swim on the beach, or why don't I run on the beach as long as possible and then swim as short as possible, right? So that would be the minimum possible amount of swimming you could do. But it turns out that that's going too far out of your way. So it turns out that the best approach is a Goldilocks approach where you split the difference in some ways in that you don't try to go in a straight line. You do take advantage of the fact that you can run faster than you can swim, but you can't also go too far out of your way. So it turns out the very fastest approach is like this. That will be the way to get to the swimmer in the least possible time. Okay? So you notice there that there's a bend in the path, and that's exactly what light does as well. Okay? So let's draw it in for our situation. So for light, we have to figure out what's the analogy for beach and sand. Well, you can run faster on the beach, so the n is actually smaller. Because remember, n is the divider. Whereas if you're going, you can swim slower in the water, then n is larger. You have a larger divider. So this would be your incident, and this would be your transmitted value when you're going from one material to another. So if you have a light beam that comes in with some incident angle theta I with respect to the normal, it will bend in exactly the same way, which is to say toward the normal. It'll bend like that. The principle of least time. So you could write it like this. You bend towards the normal. Another way to write it might be that if you're going into a higher end, your angle will be smaller. So if your nt is larger, your theta t will be smaller relative to the normal. You bend toward the normal. So that's what we'll see, and I do have a demo for you so that I can show you this in action. When light passes into a material that it moves slower in, it will generally bend toward the normal. Okay? So if nt is larger than n where you're coming from, and I, then the angle will be smaller. Are there any questions so far? Okay, so of course you can have the opposite case. I'll try to find a different nice pen here. So let's say that on this particular beach that we go to, sometimes the lifeguards are staffed with humans, sometimes they are rescue SEALs that are trained to go and pull out drowning swimmers. So I'm going to try to draw a seal here. This is not going to go well. That's looks like not a seal. I don't know if you can even tell which is supposed to be which end is supposed to be which. But in any case, a rescue seal obviously has the exact opposite problem, right? A seal will flop along very slowly on the beach, but then in the water will move very fast. So for the seal, Ni is bigger and Nt is smaller, right? Remember, the N is the divider. So if you can go faster in a particular medium, then N is smaller. So there, of course, the seal should kind of do the opposite approach. So don't try to go in a straight line because that's not taking advantage of the situation. Don't try to go too far out of your way, but split the difference, do something like that. So spend a little bit less time on the beach, a little bit more time in the water. but don't go too far out of your way to minimize the time on the land, because you're going to go too far out of your way. So we can also apply this to light. So I guess kind of put this a little bit awkwardly big, but let me try to cordon this one off. So if you have a higher end, and then you're going into a lower end, light will bend away from the normal. So it looks like this. Theta I, theta t. So when light goes into a material where it can move faster, it tends to also bend away from the normal. So this is bend away from the normal. When nt is smaller, theta t will be larger. So I want you guys to really get these two things just on a conceptual level. So they're kind of down pat, because they're very useful kind of conceptual things for many problems, so that you kind of know what to expect. And I guess the one more thing that I would like to add about all this bending business is that this bending only actually starts to happen only if the incident angle is greater than 0. And let me show you why. Let's say we had a drowning swimmer, and then we had the lifeguard right here. Well, of course, at that point, what's the least time is also the least distance, right? The way to get there quickest is simply just to go in a straight line. Anything like this would be just silliness, right? Because now you are traveling more distance in both of the things that you are going through, right? You don't have a choice. You can't make one shorter with the other longer, right? And if you're directly across from them, the only thing you can do is make both distances longer than they already are, okay? So here, for something like this, the shortest time happens to be the shortest distance already. In this case, okay? So we're not going to see the bending. So if we have, for instance, ni and n sub t, it doesn't really matter which one is bigger. If you come in at 0 degrees to the normal, you will also exit at 0 degrees to the normal. So just straight line. There's no bending at that point. So at this point, with all the conceptual things that I've told you, I'm going to write down the law of refraction, and it'll have these features, and hopefully that won't come too out of the blue. It's the law of refraction, and its official name is Snell's law. S-N-E-L-L, Snell. So here's the law. It looks like this. So it's a relationship between the incident index of refraction and angle and the transmitted index of refraction and angle. Now there's sine functions in here, but the sine functions really are almost obscuring the simplicity of it, because I want to point out that the range of angles we can have here is 0 to 90. That's kind of it, right? You can make an angle with respect to the normal that's 0 or 90, but it can't go any bigger than that. And the sine function, if you plot sine of theta versus theta, while we of course know that sine oscillates back and forth, it doesn't between 0 and 90. 0 degrees and 90 degrees it's basically just grows. Okay? So between 0 and 90 degrees, if the angle is bigger, the sine of theta is bigger. So what I would suggest to you is if you're looking at just relationships, you can kind of just say ni theta I is sort of nt theta t. So the sine function, of course, makes it perfectly correct, but it's really just thinking of it as the product of these two is sort of conserved. And you can see that that feature, and you guys know that squiggle is sort of goes as, sort of, approximately, not really, but kind of goes like that. You know that symbol? Okay. So you can see what we said, right, is if the n value gets larger, theta gets smaller, right? Or vice versa. It's because you can kind of think of it as like you have to have this conserved with this, right? And likewise, if the incident angle is 0, then the transmitted is 0. So that's what we said over here, that there's no bending. You come in at 0 degrees to the normal, you go out at 0 degrees to the normal. Okay? So that's kind of the law of refraction, or Snell's law. By the way, if you don't like my explanation of the lifeguard saving the swimmer, another explanation that people like is thinking about it as like a car. So you have a car that you drive like this, and let's say you drive from like road to gravel, right? Gravel, you travel slower on gravel, so the n value is larger. Imagine coming in at an angle. One wheel is going to hit first. So this wheel is going to run in first, and it's going to jerk you around, and it's going to redirect your path. So if you hit this wheel first, like this, it's going to kind of jerk you around and have you follow a different path. If you ever clipped one wheel on a parking block or something like that, you know that your car can get violently redirected if one wheel hits something and the other one doesn't. So that's another way to kind of think of it, a way to visualize refraction. If you're going from a material from one to the other, why you can kind of get bent in one direction or another. Of course, if you drive on gravel and both wheels, or drive on a road and both wheels hit the gravel at the same time, like this, then of course you'll continue forward, right? So again, the bending only happens if your angle is greater than 0. Okay, so let me show you this, I guess, in practice. So let me pull out the demo. I'm going to have to turn off the lights for this. Okay, so first of all, let's see if that's showing up on the camera. Is that not in the... I tried it before and it was working. Maybe it's too dark actually. Let me turn on one more light in the back or something. No? That's the wrong one. Which one do I want? Any better? I just tried this and it worked. I think that's going to have to do.
Kind of see this part, right?
Oh, I only need to see the circular part, so that's fine. Okay. Well, let's go with this. So what I have here, this is a circular kind of just chamber. There's air in the top half and water in the bottom. So I shoot the light here in. I shoot it straight in at 0 degrees to the normal, and it comes out at 0 degrees to the normal. So let me start some bending. So I'll change this to about 20 degrees coming in. So that's about 20 degrees, and it does not go out. It bent toward the normal. Can you see that? Let me make it even bigger. This light seems to be not nearly as bright as I had hoped. Oh, I think it's hitting the edge. Let's try to go with this. Okay, do you see it bending? Okay, so light's bending toward the normal. I think probably the problem is I put in water here that was too high temperature, so it's fogging up. So let me see if I can fix that. So you see it bending there? Bending toward the normal? So when light goes from air to water, it bends toward the normal. Okay? The other case that I wanted to show you was bending away from the normal. Okay? So obviously it's hard to get the water into the top half just suspended there with the air on the bottom. So instead I'm just going to shoot the water up, the light in from the bottom like this. So something like that. So again here you can see basically if I shoot it straight at the surface it will go straight through. The bending only happens when you start to deviate from the normal. So if I go like this, I'll shoot it in at 20 degrees and it comes out about 30. See that? Okay. So it's bending away from the normal. And if I keep going, I'll shoot it in now at about 35 degrees and it's coming out at around 50 degrees. So it's bending away from the normal. See that? So this brings up an interesting point. If the light bends away from the normal, at some point what happens if you get the outgoing angle to 90 before the incoming one does, right? Because the outgoing is always going to be larger. So what happens then? So here, we're almost there. And notice that now, the incoming angle is so big, there is no refracted beam anymore, right? So you can see there is no light coming from the water up to the air. This is a point where I can remind you, of course, that whenever light hits a surface, there will be generally some light that is both refracted and some that's reflected. Here, there's only reflected. This is the phenomenon I was talking about earlier, where it's totally reflected. I can put my finger right here, just where the light is hitting the surface, and notice my finger is not lighting up. And the reason why is that the light is totally bounced back inward. It's not passed out at all. So if I dip my finger just a little bit into the water, you can see it light up. The beam is there, but it never exits the water. If I pull my finger out of the water, it doesn't light up. So that's one of the things we do have to look at, is this idea of total reflection. Now I should mention that this is where it starts, but so here you can see we're at an angle, incident angle that's not big enough yet, so the light is still passing out. It's still refracting. Here we achieve that state of total internal reflection, and if we make it even bigger, we just maintain it. Okay? So there is a whole range of angles where total internal reflection occurs, and we're going to find the equation for where does it start? Where does the party start for total reflection? Okay? After that, it just continues. All right? So those are the couple orders of business we have to do. Figure out what's up with this total reflection or total internal reflection, and a couple other things. Are there any questions on this before I put the demo away and turn the lights back on? Yeah.
So what if the light can't escape? Is it still going to refract? Like the ocean, for example, like it would go to the bottom only, but...
Okay, so with refraction, remember that this whole phenomenon of not being able to come out is only when you're in a higher end material trying to come out into a lower end material. So you couldn't have this going from air to water. You can only have from water to air. So it is possible that you can't see something underwater because the light can't escape. So that's one of the examples. I'll do it just a little bit. Yeah, question?
So if you have like electron, does electron change its pathway in the water.
The electron?
Yes.
You mean how is this light generated?
Oh no, I mean, it's photons, right?
Yes,
Like it's,
not
what if
electrons.
it's an electrons? Like, do they change the angles?
So anytime light is traveling in a material, the way that that's happening is that light, which we'll learn later can be thought of as photons, are absorbed and re-emitted by the atoms in the material. So that's what's responsible for the transmission of light in the first place in a material, and is responsible for the reflection and refraction, is the light interacting with the material. If you had light just traveling through a vacuum, it would not spontaneously reflect or refract. It has to interact with the material. Does that answer your question?
I was talking. I was gonna ask, like, so we had an electron beam in the lab, the previous lab, I think, and so if you have like an electron beam in the water, it's gonna change like path in the, it kind of bends just like that.
Well, the reason why the beam bent in your E over M lab is because of the magnetic field, right?
Yes.
But the light the reason why you could see the electron beam is that those, the collision of the electrons with the gas molecules inside the tube gave off light. So you could theoretically have an electron beam through water, but that's much harder to get them to continue to go through there. You would tend to stop them much more, right? So I'm not sure what that. Does that answer your question?
Yeah.
Okay. Okay, so let me put this guy away. Turn the light back on. Okay, so at first, I just wanted to kind of jump ahead and show you the total internal reflection bit so that I didn't have to put the demo back out. But before I even do that, let me just give you a couple commonplace examples of refraction. One of which is if you've ever looked at a body of water from the side, it always looks shallower than it is. I know I have this issue when I'm trying to make pasta and I'm filling up like a pot of water, and so I fill it up. I say, okay, that should be deep enough to fit my spaghetti or whatever. I put it on the stove, and I go, that's not enough water. And then I, of course, realize that I'm looking at it from a kind of an angle, and I think it's shallower than it really is. Okay, so that's due to refraction. So if you, for instance, have a body of water, I guess like something like this. I'd say it's like a wishing well, so there's a fountain with a coin in it. And here's you, your eyeball on the side here, looking at this. So normally, of course, if you're looking at something, if it's not its own light source, the reason why you're looking at it is because it's reflected light off of it, and that light is now getting to your eye. So normally, you would be seeing it because it would get directly to you, something like that. Now, of course, that's not going to work here because the path of that light in going from water to air is going to bend. So if we dropped in a normal here between the water and air, the light beam is actually going to bend away from the normal, like that. And that light beam that would normally go into your eye is actually going to hit you somewhere in your midsection instead. Well, luckily, of course, light beams from the coin are going out in all directions. That's why a bunch of people standing around the fountain could all see the coin. So we're just going to have to grab another light beam. So here's a light beam that would normally have gone way up into the sky and not into your eye, and you would not have observed it. But this one, in bending away from the normal, bends just right to actually get to you. So you do still see the coin, but you're getting a different light beam than you would have otherwise. So light is being bent away from the normal as it exits the water into the air. Now here's something you have to understand about human perception. As much as we might know the science and know better, everything that goes into your eye, your brain thinks came directly from the source. Okay? So you don't know any better. Everything that you see, you perceive that it is coming directly in a straight line from wherever that was. So your brain does not think that the coin is over here. It just takes this distance and maps it over here. So the exact same distance, but like that. So your eye will always think that the light is coming directly from the source without any bending. And that puts the coin, as you can see, far shallower in the water. And that would apply to not just that coin, but any coin, or even the bottom of the fountain itself. So it's going to make you think that this fountain is shallower than it really is. Okay? So again, because the eye thinks that, well, that's a weird way. The eye doesn't have a brain, but I guess your vision sensors thinks that everything entering your eye arrived in a straight line. Straight line from the source, when, of course, light can bend. So that makes you think that some bodies of water are more shallow. Another example of this, if you've ever been talking to someone across a campfire, right? So a campfire heats up the air, and when you heat up air, it tends to have different values of the index of refraction, so you tend to see the shimmering, right? Now, of course, you can't really see air. Air is invisible. But what you're seeing is the light going through that being bent in unexpected ways. That's also why you can see glass, for instance, why you can tell that you have a glass container. Glass is mostly transparent, but it bends the light of the things going through it, so you basically see the glass because of the things that are behind it are warped and distorted. If you've ever tried to look at water, a piece of glass underwater, it's far harder to see because the bending between water and glass is not as much. So this is a problem if you still wash your dishes in the sink, right? And you're trying to find something underwater, right? Has anyone ever experienced that?
Like a glass plate or something.
Yeah, exactly. You're trying to find a glass plate underwater. Where did that thing go, right? In fact, it's possible to put glass into a liquid which has exactly the same optical properties, same index of refraction, and get it to disappear completely. So there'll be a photo of such a thing on your homework 8 where you can actually literally see glass disappear because even though you have glass has an index of refraction that's higher than the air, you can also put it into something that is very similar. That does bring up one point I think I forgot to mention that if it's not already obvious from this formula, that we talked, of course, about bending toward and away from the normal, but we can also talk about it as a matter of how much, right? So the more the n value changes, the more the angle will change, right? So the idea is that if n changes more, the angle changes more, either towards or away from the normal. So that's kind of a corollary to this law. So if you have a very subtle n difference, the light will bend a little subtly. If you have a huge n change, the light will bend a lot. Or you can go in the other direction, and you can even say if there's no n change, then you will have no bending. And so if you put, say, a glass object into a liquid with the same n value, then there will be no bending of the light when it goes from the liquid to the glass and back out, so that makes it so that you basically can't see it. Okay, so this, hopefully you've seen this at some point. If you're looking at water from an angle, it looks shallower. You may even have been waiting around yourself, right, in a wading pool or whatever, and look down at your own legs, right, and seen that they're kind of short and stumpy. Okay, so again, that's just refraction. Let me show you another example of refraction real quick. These are responsible for what are called mirages. So optical illusions. So here's an example of a common one that you may have seen. Let's say you're standing out in the far East Bay where it gets real hot or something like that, and you're just standing by the side of the road as cars drive by. So what you have, light, let's say, that comes off of the car, and light that would angle down that you wouldn't normally see. And here, probably that analogy with the driving analogy with bumping against the parking block that I was talking about earlier. That's probably the easiest way to analyze this, because here, where the border line is between the surfaces is much more fluid. What I'm actually going to look at is the index of refraction of the air here, and it's going to not be a continuous border between one air and another air. It's going to be a continuum. What happens is that higher temperature, if you have really hot asphalt, then it heats up the air considerably. And you can probably know that if you heat up, you probably know that when you heat up air a lot, what happens to its density? It decreases, that's right. So if you have much less dense air, do you think light can move through that easier, or is it more difficult? It's easier, right? More empty space. So what we have is a fairly small index of refraction that will then increase from here. Right? Remember, n is the divider, so if light can move very fast through something, the n value is very small. Okay? So the hot air has a smaller n than the cool air above it. Okay? So this is cool air where light travels slightly slower, so V is slightly slower. So if we kind of imagine the light as kind of having some width to it, we'll find that the light, so I guess I can kind of imagine that some kind of draw the light as kind of marching soldiers here. We call these wave fronts. These are kind of crests that are side by side that we're kind of marking off. What's going to happen is something like this. So what happens is that the light that is closer to the ground travels faster, and it kind of causes the whole thing to curve. So kind of imagine it like as if you had a car where one wheel was on gravel and one was on the road. Okay, so you get it to curve. So like the left side of the car was on one material and the right side was on the other. So it's going to kind of scoop the light up like that, because the light that travels close to the ground travels faster, and the light that's above the ground is slightly more above the ground is going to travel slightly slower. So it tends to bend the light, and again, your human vision thinks that whatever is the instantaneous direction that it entered your eye, that's where it came from. So you can see the car, maybe not the whole car, this is an exaggeration. Usually you only get the tires. Does anyone ever see the kind of shimmering kind of tires being drawn down to the road? Or maybe if there's no car there, you might just get a little bit of the blue sky that's below the road. Ever seen one of these? These are really common on a very hot day. You can see these kind of glassy, kind of blue sky below the horizon. And maybe if there's a car there, you get like the tires kind of drawn down and stretched down below. This is called an inferior mirage, and inferior because the image is below the actual thing. This is what's responsible for the classic desert mirage, right? So in Looney Tunes, you hallucinate some kind of palm tree or something like that. That's obviously an exaggeration. But these are very real things, because in the desert, obviously, it's just like hot asphalt. It tends to heat up the air that's next to the ground. And so what you'll see is, oh, look, there's a lake over there, and I'm going to go there. I'm really thirsty. I'm in the desert. but of course what it really is just a patch of blue sky that is below the horizon. So any blue that you see below the horizon, you made a mistake for a body of water. So you'll never actually get there. And these can be quite convincing. Okay. You have to go out to where it's really hot to see these, but we do get the opposite kind in the Bay Area because we experience what are called temperature inversions. So in the Bay Area, we're of course much more likely to get fog next to the ground, right? So we get cool air here, fog and whatnot, and then higher temperature air, hotter air above. For instance, if you go up to the top of, like, say, Twin Peaks in San Francisco in the morning, you can often look down and see the whole city coated in fog while you're in the sun. The reason why this is called a temperature inversion is because it kind of reverses the normal progression. Here, you have the hottest air near the asphalt, then colder air above, and then, of course, just keeps getting colder as you go up towards space. Whereas here, of course, it's cool on the bottom, then hot, and then, of course, colder when you go way up. Okay, so it's kind of a shift in the order. That's why it's called the temperature inversion. It's a shift. It's like these two kind of should be reversed in order for it to be a smooth progression from the ground up to space. So what can happen here is this. If you have, say, some kind of object, whatever, a ship or something out, that's of course one of the reasons why we get the cool air is near the ground because of the ocean. So if you get a light beam coming from that, it'll bend the opposite way. So the slightly warmer air is above the ground, and so that travels slightly faster. So there, you might say, well, what's the point of that? It kind of just hits the ground for you and doesn't get to you. But we get a very interesting thing. Let's say we have a ship that is normally can't see it because it's beyond the horizon. But if conditions are just right, you can actually see it from beyond the horizon. And where will you see it? You will see it wherever it is that light comes in. You'll see it up here. So it's possible to see things from beyond the horizon above their actual location. This is called the superior mirage because the image is above where the actual object is. And by the way, these are very real things. You can just as easily capture them with the camera as with your eyes. You can take photographs of these things. So if you told your friend you saw a floating ship and they don't believe you, you can just take a picture. They think this is where the old legends come from like flying ghost ships. They were just regular ships that were beyond the horizon, but you see this weird shimmering ship above up in the sky. Okay, the Flying Dutchman and whatnot. Okay, and they are shimmery, of course, because the atmospheric conditions aren't stable. Right, they're not going to give you a perfect image. In the Bay Area, one of the applications of this is, you know, the Farallon Islands off the coast here. They're what is it, 20-something miles. They're not easy to see. But some days they look bigger than others. And the reason they look bigger than others is because a temperature inversion is helping to bring some of the islands up. And so you can see more of them. You can see more toward the bottom than you would otherwise. Okay, so those are some examples of mirages where light bends based on the index of refraction. And the final order of business that I would like to at least get into today is the total internal reflection. So TIR, total internal reflection. Now at this point we already understand a little bit about the parameters for how that happens. First of all, you're only eligible to have that happen when you are in a higher end material trying to escape towards a lower end material, because the whole idea is that light bending away from the normal is how it works. Because what happens here is that the light bends so far away from the normal that you don't actually escape. So it kind of goes like this. If you have a small angle, light bends away from the normal. If you make that angle bigger, then light will bend even more away from the normal. And if you make that bigger, then at some point, you bend so far away from the normal that you actually never make it into the second material. So that is where I'm interested in talking about this and this. So notice that as I increase the incident angle, I'm increasing the transmitted angle, and at some point, when I increase the incident angle, the transmitted angle increases, and at some point, the transmitted angle goes to 90, which is to say that it actually bends so far as to not really make it into the second material at all. The name for the incident angle at which this occurs is called the critical angle. So let's go ahead and bring out our law of refraction and just write it down. Looks like this. So when the transmitted angle goes to 90, the incident angle has reached the critical angle. Now sine of 90 is actually 1, so we can solve for the critical angle, or at least the sine of it. It just looks like this. So that's called the critical angle, and this is how you calculate what's the minimum angle. So theta critical angle, that's the minimum angle for total internal reflection. As I showed you in the demo, any angle bigger than that will also do just fine, because once you've achieved total internal reflection, you'll just continue to maintain it. And again, let me remind you, while I'm writing down all the things about total internal reflection, is that it requires that NT is bigger than NI. Okay, it requires, NT is smaller than NI. And that is why they call it total internal reflection, because usually this larger N is like some kind of material, so internal. And then this might be the outside world, say air, which has a smaller N. So this allows you to keep 100% of the stuff inside. Now, lest you worry about this weird thing skimming along the surface, I should also tell you that this is also the exact moment where this beam ceases to exist. So no energy actually goes skimming along the surface. And we have to remember, of course, that while we haven't been drawing it, there is still a reflected beam. So 100% of the light will be reflected, and the moment that the refracted beam couldn't escape, it just ceases to exist. Okay? So we have this weird situation where we would have a beam that goes here, but it turns out that that takes the opportunity to not exist. Okay, so I'll finish this up next time. Looks like we ran out of time just a little bit. I'll finish up total internal reflection and then one more topic in homework D.